We've all been there, struggling to build a speculative world from scratch, unsure where to start. But don't worry. With these 5 key tips, the process will feel much easier, and you'll be well on your way to creating your own speculative evolution world. As your Hive Guardian, I'll be your guide through this journey. So, get ready, take notes, and let's dive into the essential tips to bring your world to life. Every creature exists for a reason, shaped by the world it inhabits. A biome-first approach ensures that every species has a purpose, a role dictated by its environment. A biome isn't just a setting, it's an ecosystem governed by climate, geography, and dominant life forms. It defines the rules of survival, determining which resources are available, what threats exist, and how organisms adapt to overcome them. Survival isn't random. It's a response to the challenges of the environment. Every species must adapt to its surroundings, developing traits that help it navigate obstacles like extreme temperatures, scarce resources, or deadly predators. Example: wetlands. A wetland is a world of constant flooding, high humidity, and lurking aquatic predators. Creatures that thrive here evolve accordingly. Capybaras use wetlands for feeding and safety, taking advantage of both land and water to evade predators. The same principle applies to Arthronia. In the acidic swamps of Arthronia, the swamp grasshopper has evolved specialized feeding adaptations to survive on the high acidity vegetation that other creatures can't digest. This adaptation gives it an ecological niche, ensuring its place in the food web. What wouldn't make sense? Not all ideas align with their environment. Imagine a giant, fast-moving insect in a scorching desert that requires constant hydration. It would perish almost instantly, succumbing to dehydration and overheating. Nature doesn't allow contradictions. That's why a biome-first approach isn't just about creature design. It's about world building that makes sense. Realism is what makes speculative evolution compelling. Even the most alien creatures should feel grounded in science, shaped by logical adaptations that emerge from their environment. Without realism, speculative creatures become nothing more than random monsters. Visually interesting, perhaps, but lacking the depth that makes them believable organisms. But realism doesn't mean a creature has to exist on Earth. It simply means it must follow scientific principles. Evolutionary plausibility, biome consistency, anatomical feasibility, ecological roles, and energy efficiency are the foundation of every functional organism. Without these, a creature becomes just a fantasy rather than a truly speculative life form. Evolutionary plausibility. In the real world, organisms evolve gradually through natural selection. Adaptations don't appear just to make a creature look cool. They exist because they offer a survival or reproductive advantage. Every trait an organism develops is shaped by pressures from its environment, and nothing appears out of nowhere. A great example of this is convergent evolution, when unrelated species develop similar adaptations because they face the same environmental challenges. Sharks and dolphins are a classic case. One is a fish, the other a mammal, yet both have streamlined bodies, perfectly designed for efficient swimming. The ocean demands this adaptation, regardless of lineage. The same principle applies to Arthronia. The giant oarsman, much like Earth's aquatic predators, evolved a sleek, muscular form to glide effortlessly through the water. This wasn't a random mutation. This was necessity in action. But what wouldn't make sense? Imagine a herbivore with venomous fangs. Venom is an energy-intensive adaptation, primarily used for predation, not defense. Evolution is efficient. It doesn't grant traits that have no purpose. If a feature doesn't contribute to survival, it simply won't last. Biome consistency. A creature must be built for the world it inhabits. If it doesn't match its environment, it won't feel realistic. Think about life in a scorching desert. Water is scarce, so survival depends on extreme adaptations. Many insects here have hard, waxy exoskeletons to prevent moisture loss. Most are nocturnal, avoiding the brutal daytime heat. Now imagine a giant, moisture-dependent slug trying to survive in these conditions. It wouldn't last a day before drying out and dying. The tundra presents the opposite problem: bitter cold and relentless winds. Animals here are built for insulation, with thick fur and fat reserves to trap body heat. A hairless mammal, completely exposed to the freezing air, simply wouldn't make sense in such an environment. The same logic applies on Arthronia. The swamp ant has webbed feet and a specialized respiratory system that allows it to survive in flooded environments. But if it lived in a dense tropical rainforest, these adaptations would be useless. Stealth and climbing ability would serve it far better than webbed limbs ever could. Anatomical feasibility. A creature's anatomy must follow the laws of biomechanics and energy efficiency. Evolution never creates unnecessary features. Every part of a creature must have a functional purpose. An animal's limbs and body structure must be suited for movement. Long legs enhance speed, fins allow for smooth swimming, and sensory organs are placed strategically to optimize vision and perception. Even metabolism plays a role. Larger animals often have slower metabolic rates to conserve energy. On the other hand, unnecessary limbs waste energy. Overly large or heavy structures collapse without proper support, and features that exist purely for aesthetics, with no evolutionary benefit, wouldn't survive natural selection. Take flying creatures, for example. Real flyers have large wingspans, lightweight bones, and powerful chest muscles to generate lift. Now imagine a gigantic armored bat with tiny wings. No matter how visually impressive, it simply wouldn't be able to fly. Its heavy body would weigh it down far too much. On Arthronia, the Toxothyrus acidiflorus follows these rules. Its lightweight metallic wings aren't just for show. They allow for efficient gliding, reducing energy expenditure while soaring through the air. Every adaptation has a reason. Ecological role and food web integration. No species exists in isolation. Every creature plays a role in its ecosystem, interacting with other organisms in ways that shape its survival. Whether it's a predator, a scavenger, or a decomposer, a species must have a niche that makes sense within its food web. An ambush predator needs an efficient way to hunt, using patience and stealth. A scavenger must be fast enough to reach carcasses before competitors. A decomposer plays a crucial role in recycling nutrients, ensuring the ecosystem remains balanced. But a giant, energy-hungry hunter living in an environment with very few prey animals, that would be a disaster. Likewise, a slow-moving scavenger trying to compete in a high-speed competitive ecosystem wouldn't last long. Arthronia's ecosystems follow these rules. The poison-wing butterfly caterpillar fills a critical niche by consuming toxic plants that most herbivores avoid. Without it, these plants would overgrow, disrupting the balance of the swamp. Every species has a role, and removing one can have drastic consequences. Energy efficiency and metabolism. Life is a delicate balance of energy. The more extreme an adaptation, the more resources it requires, and if a creature can't sustain its energy needs, it won't survive. In cold climates, animals slow their metabolism to conserve heat. In deserts, creatures stay inactive during the hottest parts of the day to prevent dehydration. Without these energy-saving strategies, survival would be nearly impossible. But a giant predator that never stops moving and never needs to eat, That defies basic biology. No creature can function without fuel. In The Future is Wild, the ice stalker moves slowly and hibernates, conserving energy in its frozen habitat. It doesn't waste movement. It acts only when necessary. On Arthronia, Formicoraptor ants follow the same principle. Instead of blindly chasing prey, they rely on pack coordination, hunting with efficiency rather than brute force. Every action they take is calculated, ensuring they expend as little energy as possible while maximizing their success. Realism isn't about restricting creativity, it's about making creatures feel alive. A well-designed species isn't just a collection of interesting traits. It's a product of its world, shaped by its environment, its struggles, and its role in the ecosystem. Creating a realistic speculative world isn't just about designing fascinating creatures. It's about crafting a living, breathing ecosystem. Every species must have a role in the food web, interact with other organisms, and adapt to environmental pressures. Instead of designing isolated creatures, think about how they fit within a broader biological network. Consider what the creature eats, whether it is an herbivore, a carnivore, or perhaps a scavenger. Think about what eats it, whether it has natural predators, parasites, or decomposers that break it down after death. Examine how it reproduces and competes for survival, whether through mating displays, territorial dominance, or social cooperation. Finally, analyze its impact on the environment, whether it shapes landscapes, forms mutualistic relationships, or influences the survival of other species. The food web, who eats who? Every ecosystem is structured around trophic levels, which dictate the flow of energy through the food chain. At the foundation are producers, such as plants, algae, and other autotrophic organisms that convert energy through photosynthesis or other means. Primary consumers rely on these producers for sustenance, feeding on leaves, fruits, or plankton. Above them, secondary consumers prey on smaller animals, filling the role of omnivores or small predators. Tertiary consumers sit at the top, reigning as apex predators that dominate the food chain. Finally, decomposers such as fungi, bacteria, and scavengers break down dead matter, recycling nutrients back into the ecosystem. In a real-life rainforest, towering trees, vines, and mosses act as producers, absorbing sunlight and anchoring the ecosystem. Insects, deer, and monkeys serve as primary consumers, feeding on plant matter, while snakes, carnivorous mammals, and birds of prey function as secondary consumers, preying on smaller creatures. At the top of the chain, jaguars and large constrictor snakes act as apex predators, while decomposers like fungi, bacteria, and scavenging insects ensure no energy is wasted. On Arthronia, the towering giant grass serves as the primary producer, sustaining the Aegis butterfly caterpillar, a herbivore that specializes in feeding on its foliage. However, this caterpillar is not safe from predation. It is hunted by the formidable savage ant, a ruthless predator that dominates its terrain. Even the savage ant is not exempt from nature's cycle, as its body is ultimately broken down by the Mycetomolopsis arborifagus, a decomposer that ensures nothing in Arthronia goes to waste. Without a structured food web like this, an ecosystem cannot function. If an apex predator rules over a habitat without sufficient prey to sustain it, the system collapses. Energy flow and population balance. Ecosystems operate under strict energy transfer rules. Only about 10% of the energy from one trophic level moves up to the next, with the rest lost as heat or used for metabolism. Because of this, producers must always outnumber consumers. Otherwise, the food web becomes unsustainable. A planet with abundant plant life can support large populations of herbivores, which in turn sustain a diverse array of predators. In contrast, a world teeming with massive carnivores but lacking herbivores to support them would quickly collapse, as these predators would have no food source. Symbiosis and species interactions. Ecosystems are more than just predator-prey relationships. Many species form intricate partnerships through mutualism, commensalism, and parasitism. In mutualism, both species benefit, like bees pollinating flowers, ensuring plant reproduction while collecting nectar for themselves. In commensalism, one species benefits while the other remains unaffected, like barnacles hitching a ride on whales without harming them. In parasitism, one organism benefits at the expense of the other, like a tapeworm absorbing nutrients from its host. In Arthronia, the Aegis butterfly plays a mutualistic role by pollinating flowers, spreading genetic diversity among plant life. Meanwhile, the dreaded zombie fungus takes on a parasitic role, infecting insects and hijacking their bodies, draining their nutrients in a terrifying yet effective survival strategy. A common mistake in speculative design is making a species entirely dependent on a single organism for survival without considering the consequences if that species were to go extinct. Ecosystems are dynamic, and species must have fallback strategies to persist. Ecosystem engineers. Some organisms do more than survive. They actively reshape their environment, influencing countless other species. These ecosystem engineers modify landscapes, create habitats, and influence biodiversity. Beavers, for instance, build dams that transform rivers into wetlands, supporting an entire community of aquatic species. Termites construct vast mounds that regulate temperature for their colonies while providing shelter for other animals. On Arthronia, the kelp eelgrass grows in dense formations, forming the kelp eelgrass forest, a thriving underwater biome that shelters countless species, from tiny invertebrates to massive predators. A common world-building mistake is designing planets where species exist in isolation without altering their surroundings. In reality, life is interconnected. Every creature, no matter how small, plays a role in shaping its environment. Natural selection is the driving force behind evolution. It explains how species change over time in response to environmental pressures, leading to adaptations that improve survival and reproduction. If your speculative creatures follow these rules, they will feel more realistic and scientifically grounded. At its core, natural selection is a process where organisms with beneficial traits survive and reproduce more successfully, passing those traits to future generations. Over time, this gradual refinement results in species that are better adapted to their environments. 4 key principles define natural selection: variation, competition, survival of the fittest, and inheritance. Every species has differences among individuals, and because resources like food, mates, and shelter are limited, only the best adapted individuals succeed in reproducing. Their favorable traits are then passed down, shaping the evolution of future generations. But natural selection doesn't always work in the same way. There are different paths it can take, each leading to distinct evolutionary outcomes. Directional selection. Sometimes, a particular trait becomes more extreme over time because it offers a significant survival advantage. A real-world example of this can be seen in cheetahs, which evolved to be incredibly fast because slower individuals couldn't catch prey. On Arthronia, the Aegis butterfly caterpillar underwent a similar transformation. Over generations, it evolved into latum, a species that could thrive in highly acidic swamps. These changes weren't random, but a response to environmental pressures that favored individuals with better tolerance to their extreme habitat. However, Ignoring the effects of directional selection can lead to unrealistic creature design. If a predator's prey evolves stronger defenses, but the predator itself remains unchanged, it would eventually starve or be outcompeted. Evolution is a constant arms race, not a static process. Stabilizing selection. While some traits evolve toward extremes, others remain relatively stable because deviating too far in either direction becomes disadvantageous. In humans, for example, birth weight follows a stabilizing pattern. Babies that are too small or too large face higher mortality rates, so most fall within an optimal middle range. In Arthronia, giant butterflies followed a similar evolutionary path. Over time, they became aegis butterflies, maintaining a relatively consistent size. Being too large made them vulnerable to predators, while being too small reduced their ability to compete for food. Evolution, in this case, acted as a balancing force, preventing extreme variations from becoming the norm. Ignoring stabilizing selection can result in unrealistic evolutionary patterns. If a species continuously evolves toward extremes without any trade-offs, it would eventually reach an unsustainable form. Every adaptation comes with costs, and evolution tends to favor a balance that maximizes survival while minimizing unnecessary risks. Disruptive selection. Sometimes, rather than favoring a single trait, evolution pushes a species toward two extremes, eliminating the middle ground. This can lead to the formation of entirely new species. In the Galapagos Islands, Darwin's finches are a perfect example of this. Some evolved large beaks for cracking nuts, while others developed small beaks for feeding on insects. Over time, intermediate beak sizes disappeared because they weren't as efficient as the specialized forms. Arthronia's giant butterflies followed a similar fate. Some evolved into aegis butterflies, herbivores that could migrate across continents, while others became hunter butterflies, aerial predators dominating the verdant expanse. Failing to account for disruptive selection can lead to static, unrealistic ecosystems. If species never split into different forms, despite facing varying environments, their evolutionary potential remains artificially limited. In reality, nature constantly diversifies, creating new niches and opportunities for life to thrive in unexpected ways. One of the most common pitfalls in speculative evolution is creating creatures that are nothing more than terrifying monsters, beings designed purely for shock value without consideration for biology, ecology, or evolutionary history. While strange and menacing creatures can certainly be fun, they must still feel like real animals, capable of existing and thriving in their environments. But why does this matter? Realistic creatures make a world more immersive and believable. A well-designed ecosystem isn't just a collection of monsters, it's a complex network of species, each playing a role in maintaining balance. Evolution follows rules, shaping creatures through natural selection, not random exaggeration. If a species lacks logical adaptations, it risks breaking the illusion of a living, breathing world. A monster, in the traditional sense, is often created to be visually striking, with oversized claws, glowing eyes, or grotesque proportions. In contrast, a well-designed speculative creature follows the logic of evolution. It has an ancestral lineage that explains how it came to be. It fits within an ecosystem, interacting with predators, prey, and competitors. It has trade-offs, strengths balanced by weaknesses, and most importantly, it behaves like a real organism, with instincts, social interactions, and a life cycle that gives it purpose beyond mindless destruction. Designing creatures with an evolutionary lineage. Every species on Earth evolved from something that came before it, shaped by gradual changes over time. Your speculative creatures should follow the same principle. Where did they come from? What were their ancestors like? How did they change to adapt to new challenges? Without an evolutionary lineage, a creature feels artificial, as if it simply appeared out of nowhere. Whales provide a striking real-world example of this process. Though fully aquatic today, their ancestors once roamed the land. Evidence of this can still be seen in their skeletal structure, with vestigial limb bones and lung-based breathing, clear remnants of a terrestrial past. On Arthronia, a similar transformation can be seen in the saltwater ant, which evolved from Formiciraptor ants that migrated and gradually adapted to life in marine environments. This lineage explains its physiology, from salt-tolerant exoskeletons to specialized underwater hunting techniques. Without this evolutionary backstory, it would simply be an ant that inexplicably lives in the ocean, an idea that breaks the logic of natural selection. A common mistake in world building is introducing creatures that have no ancestry, no logical origin, just strange beings that exist without explanation. But real evolution doesn't work that way. Every creature is the product of countless generations of gradual change, thinking in terms of ecology, not just design. In nature, no species exists in isolation. Every animal is part of a food web, shaping and being shaped by its environment. When designing speculative creatures, it's crucial to ask, what does it eat? What preys on it? How does it interact with its surroundings? What impact does it have on the ecosystem? A species without ecological context is just an empty concept, something that looks cool but lacks substance. Consider beavers, which don't just survive in their environment, but actively reshape it. By building dams, they alter water flow, create wetlands, and provide habitats for countless other species. Their ecological impact is immense. On Arthronia, the moonlit fly larvae play a similarly crucial role. Buried beneath the soil, their burrowing activity aerates the ground, promoting decomposition and nutrient cycling, an essential function in their ecosystem. Without them, soil quality would decline, affecting plant life and the creatures that depend on it. An unrealistic mistake would be designing a creature that has no impact on its environment, existing purely as a terrifying predator, with no prey, no competition, and no ecological footprint. Real species don't exist in a vacuum, and neither should speculative ones. Trade-offs. Every strength has a weakness. In evolution, there is no such thing as a perfect creature. Every adaptation comes with costs. The cheetah, for example, is built for speed, capable of reaching astonishing velocities in a sprint. But this agility comes at a price. Its endurance is poor, and its bones are more fragile than those of other big cats. Strength in one area often leads to weaknesses in another. On Arthronia, the saltwater ant is a deadly underwater predator using precise attacks to capture prey in aquatic environments. However, once on land, it loses this advantage. It moves sluggishly, unable to evade fast-moving terrestrial hunters, making it vulnerable. This limitation prevents it from becoming an unstoppable super predator, maintaining balance within the ecosystem. An unrealistic mistake would be designing a creature with no weaknesses, an all-powerful being that dominates everything without effort. In reality, nature imposes limits. Evolution doesn't create perfect organisms, it creates ones that are just good enough to survive in their specific niche. Behavior and life cycle, making creatures feel alive. A creature isn't just a static design, it's a living thing with instincts, behaviors, and a life cycle. How does it find a mate? Does it raise its young or leave them to fend for themselves? Does it migrate, hibernate, or exhibit seasonal behaviors? How does it interact with others of its kind? Elephants, for instance, form deep social bonds, mourning their dead in ways that suggest emotional intelligence. These behaviors make them feel real and complex, rather than just large herbivores. On Arthronia, the Formicoraptor demonstrates intricate social behavior. Much like real ants and wolves, they hunt in coordinated packs, using signals to communicate with one another. This cooperation increases their hunting success and strengthens their dominance as predators. A common mistake in creature design is creating species that exist only to kill, with no social structure, no reproductive cycle, and no purpose beyond destruction. But real-world animals don't function like this. Even the most fearsome predators, from lions to orcas, have complex interactions and instinct-driven behaviors. With these 5 key tips, I hope you now feel more confident in creating your own speculative evolution world. Remember, world building is a journey, and every step you take brings your ideas to life. Don't forget to follow our social media for more tips, insights, and updates on speculative evolution. See you in the next episode.